supposed to take, but this is something that's automatically generated by the motor system, which kind of suggests that you're actually reactivating the same mechanism as when you're actually writing the figure eight, and we are imagining writing the figure eight. There are also some phenomenal effects, like people actually feeling tired when they mentally train something. There are also bodily effects, like activations of the autonomic system. There are also some studies that show that you can actually be stronger by just mentally training an exercise or lifting a weight. So when you train this mentally, you're actually able to lift heavier weights, and that's because it's probably because you reactivate the motor areas of the brain, and you train them to be either to fire harder or fire in the right order to lift this weight. And Desuty and his colleague made, this is a very old study, but they investigated mentally imagining pressing your foot to lift the weight and actually pressing the foot. And they measured the heart rate and the respiration rate. And as you can see, the lines follow quite nicely. Yeah, you don't even need any statistical measures here, I think, to see that they are actually kind of the same. And in one case, you see that the respiration rate is actually higher in the mental condition than in the actual condition. One thing you could argue, or which has been debated to some degree, is whether these reactivations are the thing that actually causes the cognitive phenomena. Are they essential for this to happen, or is it just a side effect of higher level brain structures doing the actual work? And there are some counter argument to that is, for example, patient data, where you can see that if the early sensory areas or visual areas that represent color, if they are damaged, then you won't be able to imagine something in color, because then that ability is gone. But I don't have time to go into any detailed discussion about this because time is running. So then you probably are wondering, what about those robot dreams? So now I'm getting to the dreaming part, at least, and soon we'll get to the robots as well. My colleague Serge Still and I, we went on a coffee break, and then we came up with a new idea, the inception of simulation hypothesis. So this is a hypothesis about how our simulations develop from early childhood. So how do they come about? What are the developmental aspects of the simulation hypothesis? So we argue, or as you see, it was the name of the hypothesis was, of course, inspired by the movie which stars Leonardo DiCaprio, which is about dreaming and dreams within dreams. So our idea is that one function of dreams is that they help form simulations during childhood. And we have been, or some of the reasons or arguments for this is that, for example, Rothbard's ontogenetic hypothesis, which states that young children and infants, they need to sleep a long time, and they are often in this called REM state sleep. And the reason they are that, because it has a neural function of generating more connections basically in higher cortical areas. And this is exactly what's needed to develop simulations. As you saw, we need the connections between the action and perceptual areas in the brain. So we argue that dreams can help with this. And we can see that there are correlations in the development of the content of dreams and the content of, for example, mental imagery that we can evoke during or when we are awake, basically. And our ideas here is also are also that dreams help improve the quality of simulations in certain way because of the certain properties that dreams have. So, for example, in dreams you often have more intensified emotions, which can also lead then to more activation in the brain, so more perception gets experienced and so on. So it leads to a bit of longer simulations than was possible in the waking state. Another thing is that in the dreaming world it seems like it's less constrained. Everything can happen in the dream world, and even for the infant then. So that leads to that there are new associations formed during dreams, and our idea is then that these can be tested during the waking state, and then you can prune out some of the things that you don't really need to simulate. So that improves the simulations, and then you dream of new things and so on. We were also kind of surprised because when we looked at this, there are lots of research on dreams, and they characterize dreams as simulated actions, basically. So they have similar theories that we do about simulation theories in the waking state, but there is no collaboration or no insights drawn from those two areas, basically. So we wanted to do that and take inspiration from the dream researchers and see how can this help us understand how simulations develop. And it's also the thing I usually emphasize is also that the dream state is also very good for developing simulations, because then you have a state where the body is almost fully decoupled from the world, or from the where the brain is decoupled from the body. So you can dream of things, that is, reactivate simulations without having to worry of executing the actions. So you don't have to develop the kind of mechanisms where where you suppress the action, or that it doesn't reach a certain threshold that makes you experience it. And you don't get as much sensory input that can affect or distort your simulations, because so you're in this actual simulation state, which is a good training ground for then developing new simulations in certain ways. So that's our inception of simulation hypothesis. Just to give you a brief, we have made a nice model as well. So we have two phases, basically, the inception phase and the mature phase. So the function of dreams in the inception phase is to come up with new simulations that can then be validated during waking, the waking state, or when you're awake, to make better and to make more simulations. When you reach or starting to get older, around 12 years old, then the simulations will have become so good that the role of dreams are no longer to form new simulations as such, but it's rather to improve or help other higher level cognitive abilities. So, for example, there is one theory by Antti Revonsu called the threat simulation theory, and that states that the function of dreams is to rehearse dangerous situations, basically, in the dream. So that's why we have them. And that's why it's so common to have nightmares, or more common than you think. Because you train these dangerous situations in a safe environment, and that makes you perform better. So that would be a function of dreams in the when you reach adulthood, or get older at least. So that's the basic idea. And what we wanted to do then was also to test this idea using a robot, or a simulated robot. So we started Okay, I have 5 minutes, but I guess I could minimize the time for questions. But yeah, just feel free to interrupt me, Tore, if I go over time. We wanted to test this idea by modeling the hypothesis in a robot, basically. So we looked around a bit about on also have people implemented dreams in robots, and that seemed not to be very common. We couldn't find any models. We found some computational models of sleep and the effects it has on memory and that kind of thing. But we found a science paper, a very short one, where Christoph Adami suggests that we should really think about robots that dream, and that this could actually have a good influence on their behavior when they are awake. So he said something like this: at night, the robot would replay its action and infer a model of the environment. Armed with this model, it could think of actions that would allow it to overcome the obstacle, perhaps trying out those in particular that would best allow it to understand the nature of the obstacle. So it could be very successful for a robot to dream of different things. We had this simple epoch robot in our robot model. So it was just a kind of simplified proof of concept experiment. The task of the robot was to learn how to simulate a very simple environment, a square environment, a maze, very simple. And the question was, would these robot dreams facilitate the learning of the simulations while it's awake? So is there any advantage in the learning of simulations to dream? And since there were no other robot studies on RoboDream, we had basically nothing much to base our implementation of what dreaming would be for a robot. We have some information about the content of our dreams and how they are. And they are, for example, they are distortions of reality sometimes. You often have perspective shifts. So sudden shifts of tension, suddenly you're in a new place or view something from another perspective and so on. So these were the things that we picked up and tried to implement in our simple model. So we had a control condition with no dreams. Then we had distorted sensory input where we just took the real sensory input and then modified it a bit with some random value. And we also had a recombination condition where we actually switched the sensors of the robot. So, for example, sensor 7 in the dream became sensor 3. So we shifted how the robot got its input. So it would kind of model this shift of attention, we thought. And then we had another condition where we also tested whether it affected the robot if you switch between waking and dreaming in certain intervals. And what did we found? We actually found that dreaming or these robot dreams that we had, they actually suggested that the learning during waking became more effective if you had these robot dreams. They didn't get more accurate as such, but the actual learning got more effective. So we saw some simple results we got some results that suggest that this idea of robot dreams, it's not that bad actually. We can have certain advantages. So the European Commission isn't that off when they say that we should put money into dreaming robots, because there are advantages, and we can see that in our little study. So I think my time is out, but I just have some random slides that are not part of this nice narrative that I've had. But I also wanted just to mention that we have other robot studies that have investigated simulations of different kinds. So we have models of allocentric spatial knowledge, or rather how you can take somebody else's perspective and view the spatial area from that person's perspective. And then lots of studies on just learning the topological structure of a maze, like learning to navigate, and learning to navigate to a certain goal. There are some models on that. There is also some models on obstacle avoidance and problem solving. But what I would also like to say to you as cognitive science students is that there is lots of work to be done in terms of modeling simulations. There are many different areas which are still very unexplored, and what we can actually do with these kind of mechanisms. So if you want to do a master's project or something, you just give me a ring and we can start to discuss that. And these robot models, they are often quite simple as well. So we haven't, since they are usually done to actually test the theories rather than making really good robots that can